senior PhD student, hopefully graduate this year, at the City College, New York. And Sean was a participant in last year's Summer Institute at the National Water Center. So I think we're going to talk about mainly that, right? Or the project that you started at the Summer Institute. So we have kind of a tradition here that people kind of introduce themselves or give a short bio, so feel free and talk about what you do for your PhD as well. All right? Okay.
Good afternoon, everyone. I'm Shal Bafshari. I'm a PhD candidate and research assistant of Civil Engineering Department at City University of New York City College. And so my background was civil engineering. I started my bachelor degree in civil engineering department, and then my master was actually marine structure in my bachelor university, and then I came to US to pursue my master's in City College of New York, but I directly transferred to PhD program of water resources group, and I specifically work on my advisor's river network system and national and WBM plus, that is the hydrological model, and I took the part of assessing and modifying the river network system of that hydrologic model, and I specifically working on in my own study at station hydraulic geometry relation. That is the power law relationship of discharge and hydraulic components of the channel, and then from those parameters of that relationship, I would back calculate geophysical aspects of channel and each stations that are USGS station in my own study. But put that aside, today I'm going to talk about an extension of my study that I had made here last summer, being as a participant of Summer Institute of National Water Center, and I had the privilege to come here and meet a lot of fantastic people in National Water Center, and also some other participants like me were PhD and graduate students. I met a lot of friends and pursue my studies about flood mapping and flood inundation analysis to another level that I'm going to explain today. But my study domain stayed the same. That was Black Warrior River between Holt Lock and Dam and Oliver Lock and Dam. So I'm going to talk about that study that I extended to this level. So as introductory to my speech, with the growing stress of climate and land use changes in recent times, flood events are becoming more frequent in existing decades. And in the past 30 years, estimated cost of average annual flood damage is approximately $8 million US within the United States. And therefore there's a growing interest in regional to continental scale, high or hyper resolution flood forecasting and flood risk assessment across various parts of the globe. And our aim is to reduce the damage over the flooding prone zones, especially densely populated zones or urban zones. So various flood analysis and inundation mapping tools have been generated up to now by scientific communities and governmental agencies like FEMA and USGS to gain essential information in quickest way and with least dependency on spatial details. And there's an urgent need for gaining essential flood information in the quickest way without being relied on spatial details like channel geometry, floodplain cross sections, and so forth. And also incorporating the effects of existing geophysical and man-made attributes, including channel bathymetry, levee, and other hydraulic structures along the channel or beside the channel, is scarce, or is hard to be implemented in the model. So in our study, we focused on two groups of inundation models, generally semi-empirical model and physical model. In upcoming slides, I will talk in details about each of those types of models. So this is a snapshot view of physical models and semi-empirical models attributes and features. And on the right side, I would explain about the models that are belonging to either of those groups and their details and their structures. So starting from the physical models, they are labor-intensive, require many data and inputs, and is complex to set up, and are time costly to be set up. But they produce accurate results at the end. The other group that are more simpler, called semi-empirical model in our nomenclature. They are computationally simple, they are fast, require few amounts of data and inputs, and easy to set up. And they're capable of producing handy but less accurate inundation information compared to physical models. Now, starting on the right side, we had worked with one physical model called HEC-RAS 2D, that is US Army Corps of Engineers Hydraulic Engineering Center lab model developed by those people. So it's an old model back to 1990s or even older, but they started with a 1D model, and lately they produced a 2D version of that model that is implementing so many geophysical and land cover and different attributes of that domain in 2D level. So it performs 2D on a steady flow simulation based on solving either the diffusive wave or full momentum or Saint-Venant equations. It is capable of computing key hydraulic and inundation mapping, like inundation depths, flood boundary, velocity, shear stress, so forth. It allows low to high resolution DEMs to be integrated with land cover layer maps. Users are also able to add hydraulic structures like dams, levees, culverts, and modify their outline and structural details. This is also capable of incorporating multiple inflow-outflow boundaries at the upstream and downstream, or even within the computational area. Outputs from HEC-RAS 2D are high-resolution time series of flood hydraulics, like depth, velocity, at all user-defined cross-sections. Now, talking of the semi-empirical models, we applied two semi-empirical models. The first one, that is the auto route, is the more complex one in the group of semi-empirical models. So it is also generated by a US Army Corps of Engineers, but Coastal and Hydraulic Lab. It performs 1D steady-state flow simulation and uses Manning's equation to calculate the normal flow depth over a high intensity number of cross-sections. That is user-defined, but you should define steps spatial steps of cross-section. It uses a volume field numerical approach to calculate the flood extent at each cross-section. And it can quickly simulate flood inundation maps over large spatial extent. Inputs to auto route are stream flow, location of streams, and land cover maps. Surface roughness, estimate for each land cover classification that is provided by some sources like the National Land Cover Data Set. Outputs from auto route are also high resolution flood depths and flood inundation depth. So it also gives depth and maps together. Auto route automatically samples cross-section geometry and channel slopes from the topography or DEM layer and estimates hydraulic roughness for each cell of that layer. And the other second or last semi-empirical model, which is the most simplest one in our whole model cluster, is called HAND. That's an acronym for height above the near edge drainage. It is developed in late 2010 somewhere, and is a hydrological train analysis process. It calculates the vertical distance between a given cell, DEM, the nearest stream cell that it brings to, which defines the inundated potential of that grid cell. And HAND is entirely raster-based and defines the inundated zone by a river segment, and it does not require cross-section plotting as a pre-processing step, as the other two models does. So HAND method is coupled with NHT plus river, the newest version of HAND that is developed by Liu et al. It's coupled with NHT plus river network dataset to produce NHT plus HAND. And NHT plus HAND rasters were employed to estimate the stage height channel properties like velocity and other hydraulic components for different NHT plus reaches. And therefore, when it's engaged with Manning's equation, then they could calculate for each NHT segment the Q. So for each NHT segment, they could calculate multiple values of Q versus stage height. Then they can produce a rating curve. And from that rating curve, if they have a stage height value, or say Q value, not stage height, if they have stream flow value, they could back calculate the stage height, and they say, if I have that stage height, how much would inundate the surrounding DM cells. So that's how they would generate inundation maps in HAND method. So now let's be specific about our study domain and where are we going to compare these models. So starting from upper left, our study domain is here, Blackwater River, as we started to investigate last summer. And in terms of stream flow information, we simulated national water model inflows, particularly for a period of last month of 2005, year 2005, and we engaged the stream flow, particularly for that period of national water model, with USGS and FEMA information, flood information, in order to scale the national water model inflows for each segments of NHT plus to a particular flood year, like 10, 100, and 500 year flood. Therefore, we can produce, by means of those time series, flood inundation maps, particularly for those flood years. On the far right at the top, this is our study domain. You can see the NHT plus river network system. And also you can see that we have two hydraulic structures at the upstream and the downstream, but we really take care of Oliver Lock and Dam, that Holt Lock and Dam, yes. And we have a levee here that will be implemented in our model comparison. And here you can see two layers of DEM and land cover to check out what is going on here. It's a really moderate to mild slope basin. Actually, at this part of the channel, it's really mild. And you can see half of our study domain is urban, and close to half of our study domain at the upstream is somewhat natural. So we have two bunch of natural and urbanized study area that are combined together. So, and this is the another broad view of our inputs, our models, and what are expecting to receive from those models. And so our land cover is national land cover data set for 2011 version. So we are incorporating 4 different type of DEMs for that same study domain. So we have natural NED from USGS. We have bathymetry data set, thanks to Dr. Cohen, for the Black Warrior segment. We developed those in terms of DEMs along the channel and attached them to our natural NED. So we have the new types of DEM. We also have the elevation. I could capture the elevation of the crest of the levee, North Coast levee, and I just diffuse a new layer to the original NED to be included by the levee. So I have NED plus levee. And then the last scenario is all combination of symmetry, levee, and the natural NED. So it's pure, close to be realistic. And this is our inflow time series for that particular period of 2011 that I found that it was somewhat close to a 5-year flood event. So this is exactly talking about this period. So that's the time series of the NHT plus segment right at the end of our domain, where we also have a USGS station that is the red one. So we can see here that the USGS observation and the National Water Model estimation is pure, not really identical, but the Nash Sutcliffe efficiency says that they are above 80. And they have a high correlation coefficient also saying that they are close to be identical. So we have USGS station at the downstream point, and for each of those tributaries, I will explain later, for each of those tributaries, we have FEMA flood information for 100, 500, and 10-year flood events. So our goal, as I mentioned earlier, is to scale the observation for each NHD plus segment that is provided by a National Water Model. We want to scale them up into some degree that would be identical to 10, 100, and 500-year flood. So therefore, we can produce flood maps along the channel and along the tributaries for those flood years by means of the flow information provided by National Water Model. And we are using these two categories, or say 3 flood inundation models, and we want to find out whether there is a significant difference between what HEC-RAS 2D would produce and what these two simple models would produce. And at the end, we want to generate flood inundation maps and flood inundation depth and compare them together. But before doing that, I had come across a question that do we really need to take into account the tributaries contribution into our flood model comparison, or we just need to stick to the main channel? Does any of those tributaries have a major contribution to have a significant flood, while there's also a significant flood in the main channel? So in order to answer this question, I need to go back to the USGS time series for the upstream and downstream station. I was lucky to have 2 USGS stations at the upstream and downstream station. So here you have 2 blocks that are showing the USGS time series at the upstream point and USGS time series down at the downstream point. And by watching these 2 graphics, you can see that the dynamics and the time of having those peaks are identical in both of upstream and downstream. And I should say in first place that the length of the channel here is about 15 kilometers. So within that 15 kilometers, you can see that as you have a spike in upstream, you have the same spike but larger than upstream point at the same date. And each of the time resolution here is daily basis. And by means of that, I can argue that the travel time of a flood wave is within a day. But I don't know what is that, because the resolution provided by USGS is just daily basis. And I don't know at what hour of a day those flood happens. I mean, at what hour, how many hours does it take to travel from upstream to downstream? but I would answer it shortly. So, but you can see that in most of the cases, downstream station have larger amount of flow, particularly at the time of a flood event, than upstream. So it must be contributed by the lateral flow, even by the runoff, or I can say by these tributaries. Another way to speculate it is by going through the peak flows. So USGS also provides you stream peak flows. But they are not like this continuous. They are given by particular date. But I have 19 simultaneous records of upstream and downstream. And blues are downstream station records, and reds at the same time are upstream records. And in most of the cases, we have 19 cases here. 18 out of 19 shows that downstream in times of peak flows are larger than upstream. Therefore, I can say it is being contributed by lateral flows. So I should take into account the contribution of tributaries at the time of flood event. That means if I want to scale up National Water Model stream flow, I should also scale up these guys. And I'm fortunate to have it by means of FEMA flood year values. So I can scale them by means of FEMA flood year values. Back to my first, another question that I made. What is the travel time of the flood wave? So because I work on the HEC-RAS 2D and National Water Model time series are hourly basis, I give the HEC-RAS 2D, gave the HEC-RAS 2D that resolution for the time series. And the outcome of the HEC-RAS 2D is also based on that hourly resolution. And I could find out that because I have three types of flood year, 10, 100, and 500, and also I have 4 types of NEDs. In most of the cases, it took about 1.5 somewhat hour to travel from upstream to downstream. So the travel time I can speculate of the flood wave is about hour to 2 hour. And back to this point that how we can scale up the National Water Model inflows of this river network system. So let's explain in detail about the graphic. So the thickness of these blue lines is a weighted value of a flood. So or a stream flow, I can say. So they're scaled from 0 up to 100. That means, 0 to 100. That means when you have 0, there is no significant thickness. When you have 100, that's the ultimate thickness. So therefore, you can say how much of these streams will contribute to the inflow of the main channel. And if there are solid line, that means the scaling of the National Water Model inflow is done by means of information that is given by the USGS station at the downstream. And when there is a dashed line, I applied the FEMA flood year values to scale up the stream flow of National Water Model at these. So, and you can see that the 100-year flood, 500 and 10-year flood at the downstream station is about 5,300, 7,600, and 9,000 cubic meter per second. And those percentages must be, or factors I can say, must be multiplied by each of those. If you want to see, for example, for 100-year flood event, that particular thickness means 0 up to 0.51% of that value. So that will give you an estimate of the inflow, a particular inflow that is 100-year flood for that segment that has a similar thickness. And back to my HEC-RAS study, that's the snapshot view of how I can implement or engage land cover with DM. So at the right side, you see a snapshot view of a DM at this portion that is nearby North Fork levee, that is this guy. So HEC-RAS 2D is capable of generating structured and non-structured grid. For example, when you have something like this, that you really don't care about the detail of flow that is passing through the main channel in the middle of the channel, you just use the structured grid that are orthogonal cells. But when you are dealing with something like a break line or something like a levee, you may be interested to see detailed flow at this infinitesimal cells, or say small cells along or nearby the levee. And it should happen because when you have an abrupt change of elevation and you have a large cell, the flow computation and hydraulic computation must be in detail, and therefore you need to have smaller cells because the slope will change, and at the end of the day you may have some islands of water that are separated from the main channel, and it's wrong. And because you need to, you have to change the resolution to let them to be connected. And for this side, that is a land cover. So each center of the cell would capture the land cover category, and for each land cover category, we had about 14 types of cell. You have them here. For each of those categories, I assigned a Manning's roughness value that is given by Morse et al. 2015. It's made on different types of land cover chain. They had 3 types of land cover Manning's roughness, and they found one of them is the best, well adjusted with observed flow information. So I used or applied those roughness value associated with each of those land covers. And here also, that shows a snapshot view of that cross section. My purpose of putting that here is to show you how I can compare 4 different DM associations. So the solid line shows that both NAD plus levee, NAD plus bathymetry, and NAD plus levee and bathymetry are identical. So the dashed line here shows that natural NAD does not give you information about the bathymetry, so it will be smooth surface. But if I take into account the bathymetry, it will look like this. And if I don't take into account the levee, it will pass like this. But if I take into account the levee, it will go up like this. So it gives you a brief snapshot view of different, or combination of different DEM associations. And I would also say that the HEC-RAS 2D is capable of attaching different types of mesh grid size. And it doesn't mean that if you have, for example, I have a 25 by 25 meter grid cell over a 10 by 10 meter NED raster. So it doesn't mean if I have 25 by 25, I lost a lot of information. It's not the way in HEC-RAS 2D. So suppose that each side of a grid cell is like a cross-section line that would pass through the below NED. And if that NED has a finer resolution than the grid cell, so that cross-section may detect a lot of points. And that would be a kind of a cross-section at that site. And then you have a lot of information for each of those channels. So, but as you produce larger 25 by 25 cell, their center line would capture the land cover. So if you have something like here and you have a large grid cell, that grid cell would just recognize this as a whole water. But in reality, we have water, we have land, we have some other types. So the lower resolution would capture the land cover type precisely.
Sure. So on the grid, I saw that there is a triangular grid. So it's unstructured mesh. And So how did you generate that triangular grid between the rectangular grid? What is the criteria to generate this?
Good question. So in HEC-RAS 2D, you can add something called break lines. So when you add break lines, it enforces the orientation of the grid cells. You can also say, I want those grid cells that are close by the break lines to have 10 meter by 10 meter resolution, but as we go away, it will smoothly become larger and larger, becoming, say, 50 by 50. Yeah. And the other thing I may also add here is that you may be really careful about the way that you are adding these break lines. At some point, I will show you next. I had that in my mind. But before that, in order to do the comparison, we have two types. We have visual comparison of flood maps, and also we have numerical comparison. For that second part, I applied these statistics. I wonder if you had worked on either of those, but this shows their hierarchical complexity. Say, the overall accuracy is the simplest one, and therefore it's more biased than the other one. Somewhat, you may find out that overall accuracy of your two model comparison shows that the models are really identical, but in reality they are not. And why? Because it will be affected by the dry cells. So if you have a low flow event, like a 5-year flood, and all the flow would remain in the main channel, but some models will have some islands of water and they're not totally identical, but the majority of the place is a dry cell, it will take into account the number of dry cells that are reported either by both models. And that's why the overall accuracy would wrongly say the models are identical. But it's not actually. But these two other are less biased, and they are really focused on cell-by-cell comparison, and even they goes further into a detailed category, like just looking for the wet cells, not just dry cells. And therefore, they would give you less score than the other two. So now let's talk about the visual comparison. So in following two slides, I'm going to show you 10-year flood event comparison of models. So the columns are talking about model comparison, HEC-RAS versus AutoRoute, HEC-RAS versus HAND, and AutoRoute versus HAND. And each row of this plot is based on their DEM association. And as you go down, it will be more detailed. The toughest is the natural NED, and the lower one is the NED plus bathymetry plus levee. And as we go through flood years, this is the 10 years. This is 10 years, this is 100 year, and this is 500 year. As I do this quick, you will see that some associations has a wider flood inundation extent, and some other has restricted flood inundation. And some of the models, like HAND, will produce some water lakes or something like that, and that's due to the nature of HAND. And AutoRoute, compared to HAND, is much more close to be a good model, like HEC-RAS, to be realistic, I can say. And you can see for those cases that I included the bathymetry, because I changed the bed slope of the channel, and both HAND and AutoRoute are affected by the variation of the bed slope. They are more sensitive than HEC-RAS 2D. HEC-RAS 2D, due to its nature, can handle this by means of its own physics. But these two, because they are simple model and they're coming from simple Manu's equations, compared to HEC-RAS 2D that are fully dynamic models that would take care of sudden variation of bed slope, because it is working on shallow water flow dynamic model. It will respond better than these two hand and auto route. And the blue color here shows the intersected inundation of two models, and the other colors like yellow and I can see it as the purple. Oh, red. It's belong to either of those models. So the yellow here belongs to HEC-RAS, and this guy belongs to AutoRoute. And you can see at some point that HEC-RAS had the inundation prediction. AutoRoute failed to predict that, or vice versa, some other places. And I can argue that at those places that we have a less developed area by nature, they are more identical and conforming than those shallow part of the domain that are densely urbanized. And it's a messy table. It also gives you a snapshot view of those statistics for each of those blocks that you're seeing here. So that is the first block of the first page I showed you, and these are the inundation statistics. As was explained earlier, I expect to have the overall accuracy that take care of also dry cells to be the highest overall value compared to the other statistics. But it gives you a sense of which model or whether, if you consider HEC-RAS 2D as the best model, which model is more close to HEC-RAS 2D. And I found that AutoRoute is more close. And it's it was anticipated because I said AutoRoute compared to hand is much more detailed and much more advanced. But the good thing is that as we go through from 10-year to 500-year flood events, the models become worse and worse. And the reason is that for high flow values, they may be less sensitive to abrupt change. But for low flow values, the water is more confined in the main channel or in the topography. That's why you may expect to have better results for low flows. And also we did the comparison of depth, flood inundation depth, on the same platform. So for the natural NED, AutoRoute and HEC-RAS produced a similar result. But as we go through other association of DMs, if you take into account the bathymetry, and absolutely for those places we have a shallow bed, AutoRoute could not handle it like HEC-RAS. And we have a little discrepancy here. And also, particularly to those places that we are comparing hand is more sensitive to geophysical variation than AutoRoute. And you will see the colors are meaningful here. So, as we go through the warmer color, we are comparing, for example, AutoRoute with HEC-RAS 2D. We are comparing the right model, and as we're going to the colder color, we are on the right side. We are comparing HEC-RAS with other. And we see that in most of the cases, when we are talking about the natural DM, those models are somewhat close to be, their difference, the inundation depth difference, cell by cell comparison shows that they are so close. But where we are going to, as we are going through the shallower part of the channel, or where are talking about, we're talking about the inclusion of bathymetry, we see that the difference become larger. And and I also mentioned that we also want to compare our flood inundation maps that are being produced by flood models with those that are proposed or created by FEMA. And in order to do that, firstly, I need to know how FEMA produced their flood maps and what model did they use, and how, if they include, like as we did, the channel bathymetry or the levee. Therefore, if we want to compare our models with FEMA, then we should talk about one of those associations of DEMs. If they just take into account the NED, well, we need to just compare the top row with FEMA. If they take into they just took into account NED plus levee, but no association of bathymetry, we should just compare this row with FEMA. So in order to find it out, I investigated through some sources. One of them was Federal Emergency Agency FEMA 100-year flood map database. Just go into the details of those databases and find out whether they did include that channel bathymetry and other geophysical aspects of the domain. And also, I was glad to find this source, Coordinated Needs Management Strategy of FEMA, that gives you this snapshot view of the domain. So the colors give you the sense of whether they did take care of something like channel bathymetry or other geophysical aspects. So the green means that they did a lot of things for that domain. I mean, they included everything. But the as you go through orange or red, that means they're under revision. And I communicated with this agency, R4 Regional Service, whose center are located in Atlanta for this region of southeast. And they did not sharply say we did not take into account the channel bathymetry, but I could understand from their intention that for that particular domain they did not. And the channel bathymetry was not included in FEMA flood map products for that Blackwater River segment, as you see as orange. So that gave me the hint that if they produce something for 100-year flood event for that domain, they did not take into account channel bathymetry. Therefore, if I want to compare our model results with FEMA, we need to just take into account those products that are associated with NAD plus levee, because they did take into account the levee. And this is the comparison. But for flood maps, they had the whole product for the domain. But for the flood depth, they had that just for this part of the domain. So I just compared that intersected domain with our model. And you can see, as I expected, FEMA applied HEC-RAS 1D for producing the flood map. And therefore, HEC-RAS 1D and 2D, back to the color, has the similar cell-by-cell comparison. By means of cell-by-cell comparison of flood map, they have similar flood depths. And Othera took the second place, and Han took the third place in being similar to FEMA's product. And you can see that Han always has over inundation compared to the others. And this is just for 100-year flood event. So now my conclusion. I have 2 pages of conclusion. So this study describes the trades-off between various association of geophysical and geospatial details in setting up a flood inundation model and flood model responsiveness to different physical settings. And as I explained, overall accuracy and kappa statistic based on their nature and based on their synthesis has less sensitivity to real world, because it can be biased by similar dry cells that are recorded by both models, and they will wrongly produce high values of statistics. That means you must take care of other flood inundation statistics to not give any feedback on high score produced by these two less accurate statistics. So you should take care of conditional kappa and F overlapping statistics that are more sensitive to wet cells in particular. HEC-RAS 2D and AutoRoute and HAN can be ranked, as I mentioned, in the same fashion according to their model complexity to be set up, to be executed, and computational capability. Therefore, it was expected to find the most conformity in terms of flood inundation maps and depth between HEC-RAS 2D and AutoRoute, and HEC-RAS 2D and FEMA flood maps. And HEC-RAS 2D versus HAN was the worst in terms of products, comparison of products. HEC-RAS 2D demonstrated more capability in accounting physical attributes of whole domain and addressing the effects of modification to terrain models. If you have an urban zone that you are dealing with dams, you are dealing with a levee, you are dealing with some structures that are an obstruction to flow movement, you'd better to use, and you have a lower scale domain, you'd better to use high or advanced flooding models and incorporate those two simple models for large scale that HEC-RAS is capable of simulating it, but the modeler will have a nightmare to set up the model in order to be more specific. So among the semi-empirical models in general, AutoRoute was slightly slower than HAN because it's more complicated than HAN. However, resulted in more stability in conforming with HEC-RAS to be the physical and accurate model. And through all flood year scenarios and terrain associations, the semi-empirical models performed well and close to HEC-RAS 2D's inundation extent and flood depths, particularly in those places that are less developed than the lower part of the stream that is urbanized and highly developed. And the last page says that at all three flood year events, NAD plus levees association of DEM resulted the highest inundation statistics, and we can expect that because the levee would hold water to not go beyond some levels, and it will restrict the water polygon, and that means more conformity, and that's why you would expect that NAD compared to the other would give you the better answer. And terrain models which included bathymetry brought about the weakest inundation statistics, and it's due to two reasons. Because when you take into account the channel bathymetry, it produces more oscillation and then more variation of bed slope. Those models that are sensitive to bed slope, like those semi-empirical model, would produce less accurate models than HEC-RAS 2D that is based on shallow water fluid dynamic equation that would take care of the abrupt variation of water state. And also the other one is change in vertical distance between given cell that will produce absolutely in those models like HAN that are raster-based flood inundation maps, and based on the comparison of elevations of different cells nearby the other cells of the main channel. And more inconsistency in flood models was found in comparing inundation depth than a flood map. And models produced quite similar inundation depths at regions having steep bed slope and processing less geospatial variations I mentioned, less urban zone. And semi-empirical models in all these comparisons showed to be more locally affected by irregularities in geospatial attributes of the terrain model than HEC-RAS 2D. And based on what we found, given similar topological and geospatial and stream flow values or flow boundary conditions, both AutoRoute and HAN as semi-empirical models are found to be reliable models producing at some point similar inundation extent compared to those generated by HEC-RAS 2D, particularly for non or less urbanized zones that you have less geospatial variation. And but they did poorly in generating robust inundation depths per se, not map, by offering irrationally deeper flood in general than HEC-RAS 2D. They produce deeper flood than HEC-RAS 2D. And these are an excerpt of our references. It's more than that, but these are the references that I included in this lecture. So if you have any questions, please, I would be appreciated to answer. Thank you.
So Shab, you said that when you use bathymetry, the statistics was not as strong, but that's a little bit confusing. It's not mean that the using bathymetry will produce worse results, right? Or it does?
As far as I know, I found in our model comparison, if you have less geospatial variation, it shows more stability by means of all models. But when you have, based on the physics of those semi-empirical models, they will be really sensitive to geospatial variation. And when you include the bathymetry, you increase the geospatial variation. And as you have high resolution DM, 10 meter by 10 meter, that means a lot of effect of different elevation to surrounding river network, and that cause discrepancies in some sense compared to. So I can say the main reason for this is due to the hydraulic formulas that are being used by those two semi-empirical models. So hand just applies a simple Manning's roughness, or say Manning's equation. I think it's the same for auto route, but those equations will not give you an accurate answer when you have an abrupt change geospatial variation. And HEC-RAS, on the other hand, is based on fully dynamic Saint-Fanon equation that would take care of oscillations of bed levels.
Could it be that the cause of it is because this is not a natural river, so it's basically almost more like a lake than it is a river, because you have the dam and the downstream, and HEC-RAS can sort of calculate that because it has fluid dynamics.
And it's 2D, and it can take care of flow movement in 2D direction. Those
yeah,
two are just
the other two, they don't account for dams or any kind of stuff.
That's a good point. The hand does not take care of levee or the dam. The way that I give him the information of levee and the dam is by modifying the DMs that are giving them. And for those DMs that I included the levee, I just elevated the cell of those locations to some level that would produce something like a block like levee.
And also for hand, did you calculate it when you did the bathymetry? Did you calculate the hand itself, the height above nearest drainage, based on the bathymetry, or?
Yeah, based on the lower level of where the water goes. Yeah.
No, but because it's height above nearest drainage. So if the drainage is at the surface level versus 10 meters below it, that's a big difference.
That's a big difference, and would produce some biases in the model. And
Yeah,
that's
the
the
hand is.
Yeah.
Maybe it shouldn't be used at all with the.
That's why you may find some lakes somewhere that is wrong, and it's based on this relative difference of two elevations, and that caused the problem. And you remember the other people like Ryan in Summer Institute worked on something called modified hand, and they want to take care of these discrepancies that is generated by.
No, I don't think that applied to this specific problem, but yeah. Anyway, it's just a thought about that.
So, Sean, I have one question. So, the HEC-RAS 2D is a depth average equation?
HEC-RAS study.
Is depth average never strict equation, or is the U Saint Bernard equation?
Saint Bernard equation.
So it doesn't consider depth average.
It's for each cell, for each grid cell, depends on where we have the cell center.
No, I'm not asking about the cells. I'm actually asking about the basic equation. Which equation they're using?
Oh, let me just show it to you right now. If I'm going to talk about it tomorrow if you attend that other. So. This is the full Saint Bernard equation, or called dynamic wave. And here you have acceleration part, you have say on a steady part, and you have other side that if you just disregard these first two components, then it would turn to be called diffusion wave.
No, I have one question. Second equation, the momentum equation.
Yes.
Is a U is a depth average velocity, or just velocity? The U is a depth average velocity.
I think it does produce a depth average velocity for each cell. It's because it's surrounded by sides of 4 sides if it's a rectangular cell, and it will have a depth at the center, and it will compare it with the other sides, and then it will take into account for the center the average of all. Is that the way that?
I was thinking a different way. Okay, anyway. So I have one last question here. You mentioned about that it takes 2 hours to move from the one end to the other end. How do you
between
calculate
1 and
that
2 hours. What's that?
Did you calculate that based on the observation data sets or based on the model?
Okay. So because the way you can produce the outcome of HEC-RAS is either by visualization of flood wave movement and also going through the tables, you can see that the time between peaks to move from upstream to downstream in most of those cases are within 1 to 2 hours.
Yeah. What is the flooding, like the even 500-year flood event?
Okay. So this is the one that I also put it in the one of the pages. So here, so the color shows the different flood years, 110 and 500 flood years for different association of the DMs. And in all of the cases, it shows that irrespective of the DM, the flood wave travel time is somewhat similar.
How come this happened? Because if you think about the momentum, when you have 500-year flood event, you're flooding ditches, okay?
Yeah.
Higher ditches coming through, so you have higher momentum coming through. So water definitely should go higher speed. If the water speed is higher, it goes faster. And also another point I'm trying to make here, the reason I'm asking that question, I was doing some back of the envelope calculation. 15 miles, the distance between upstream and downstream, if it takes 2 hours. So that means 7.5 miles per hour, and I converted
It's
to
not
mean.
miles per
Kilometer? Kilometer per hour.
Yeah.
Okay, so 7.5 kilometers is most probably 2 meters per second or 3 meters. Very high velocity for that event. If you think about that, it's very
So
high.
you think that it's not realistic?
I was thinking if it's 4 meters per second, because I was calculating mile per hour, so it's calculate 4 meters per second. But if it's 2 meters, still very high, very high. But that doesn't make any sense, because if you think about different event, like different flooding event, 10 year, 150, 500 year, the peak move will be different. I think that the time will be different.
And does the return period affect the speed, or mostly just the amount, the intensity?
I think the momentum you have because when you have the high, think about it, if you have the high ditches, you have the high velocity. If you think of one cross section, like the upstream cross section, you have a high flow. So high flow that means if you simple equation Q into area into velocity, normally you have a tendency to get a higher velocity. So you have a higher momentum coming through. So if a higher momentum, push faster, it will be the velocity should be faster.
It could be, although I'm not sure.
Or the area maybe changes.
It's like a lake, as I said, so it may be dumping the, so it's not like the river can go up very much. So maybe
It
that's.
just spreads, so you have a loss of the
velocity momentum.
I don't know if this number is realistic or not, but that maybe that's a potential.
The point that I should make is that in order to make our model comparison genuine, I need to use similar land cover data set. And I used the land cover data set of some of other studies that I mentioned earlier, and they associated a particular Manning roughness coefficient. And they called that Manning roughness coefficient as the low roughness category. And if you apply high Manning roughness, it will resist more to flow faster. And you may find something different. But the thing I wanted to explain here is that regardless of the types of the flood year, it shows that the travel time is irrespective of
Irrespective of
the flood year.
That's what I'm thinking. I think probably have more friction in the
What
water
is the reason
column
for
and
that?
kind of things. I mean, otherwise, like, I think in terms of Olympics, in bobsleigh, just the behavior as the guy put on the sled will go faster, But fortunately, it's probably the same.
I don't know how that's possible because your flooding is coming different level, flow is different level.
Yeah. And sometimes water goes. It's not just coming up like this. It's spread.
Actually, in this case, it's in the Black Warrior. It is mostly coming up because it doesn't. The banks, as you know, are pretty steep in the Black Warrior.
In average, it's 6 meters, I think. In average, is for that particular domain, it's 200 to 300 meters wide and 6 to 7 meters deep.
Maybe turbulence can affect. There's probably a lot of things.
Yeah, but think about that. Like if you velocity gets higher, first point is velocity in cross section. If you the way you mentioned about velocity gets higher, the momentum is higher. If you push something, if you think about this is the box of water. In one there you push too much momentum, it will go faster to water.
I think you're thinking at points, but here we have a large column of, so there is a lot of more interaction than just like if you just have a marble where, you throw it down. There is a lot of interaction into the thing. It makes sense what you're saying,
Definitely turbulence will affect, dissipation rate will be different, area will be different, but on overall calculation makes
you
sense.
have frictions through the walls, as you say, if it's going up, that friction also can have effect on the speed, by having, turbulence and have backwater effect that kind of block, maybe some just, it's a PhD question for
I'll question on the slides when you show the land cover map together with the other input data to form, this one. But my question is about the land cover map input part. So this data set uses like 25 meters by 25 meters. The resolution is close to landscape images. And at this level of resolution, sometimes across the class boundaries, there will be mixed pixels. But the result of land cover products, due to they have to assign a class label to the pixel, one label to a pixel, like either it's water or forest and so on. So there may be some inaccurate boundaries. So my question is, will that higher resolution land cover or more accurate land cover product across these boundary cases will have less mixed pixels will be helpful for the model?
So I understood your question in a way that you are arguing about that, for example, for this case, our mesh grid that is overlaid at the top of a particular layer, either DM or land cover, particularly for land cover, is smaller than the size of the land cover. So the land cover are 30 by 30 meter cells, and we are overlaying 25 by 25 meter mesh grid of RAS 2D over the land cover layer. But the way that it will capture the information of the below layer is by means of these sides, and either these sides or the center of the cell. And for those locations, particularly that we have something like here, So you see that green box or green square is a particular land cover layer that is spatially larger than our computational grid cell. And but this side of the HEC-RAS grid cell would capture both of these two land covers.
My question
But
is,
it will not be affected by, particularly in terms of different cell sizes. But if you have some abrupt change, it will be affected. But for these closed,
my question is not about the different frameworks, like the cell size from like your model and the Landsat product. So my question is about the accuracy issues on the Landsat land cover product. Because this resolution is not very high, across the boundaries of different land cover types, the pixels usually shouldn't be kind of mixed pixels with mixed classes, but
you're
they
saying,
kind of
for example, maybe you have here a land, but actually it's not a land, it's
yeah.
water.
So will that kind of have a higher resolution or more accurate land cover product will be very important to improve this, or
Yeah, so in HEC-RAS 2D, I can argue not other two models. In HEC-RAS 2D, you can define user. I will explain it tomorrow if you are attending. You can define a land cover by means of given land cover layers that are raster based, or you can develop your own polygons of land cover and then say, okay, for that polygon that will cross these raster, different layer of land cover of raster, you can say, okay, whatever I have inside the main channel, just assign it as a main channel. I did this for this study, and I did not show it on this page, but just for particularly for the main channel. For the main channel, I assigned a polygon that is specified by a particular Manning's roughness, and it will not be conflicted with these parts that are shown as either land or water. But you can also, for other sides of the domain that are floodplains, you can disregard these NLCD land cover layer and define your own polygons and assign it roughness value.
Yeah. Another quick question: what is a magnetic?
Word.
You mentioned the word. Let's see if I have this word in this page. Or next slide. You mentioned as what's level for the land cover. No, the previous slide. Sorry.
Are we close?
You are using the land cover mass in a certain way. What is the attribute you use? There's a level start with MA. Magnitude.
Maybe you're talking about the roughness.
Yeah, roughness.
Okay.
So how is that defined? I only know
the Manning coefficient.
Manning coefficient.
Mining coefficients.
Yes.
So I wonder. Okay, maybe I do not have Manning coefficient here.
It's
but
just like some value weight
Just like
depending on your soil.
Is there like how different land cover classes are mixed?
So that's it. That's Q equal 1 over N S2. I make the point. And that's the hydraulic radius, and that hydraulic radius is flow area over brick. Hydraulic radius. No, this is that's a cross section. Wetted perimeter, yes. So the wetted perimeter is this.
That's like the wire resistance in electrical engineering.
Yeah, and that's flow area. And that must be multiplied by flow area, because we're talking about Q.
And also, in your evaluation, you didn't compare with some true observation data. Would that
Yeah,
also
because
be
we
a
don't have any
possibility?
flood map for this. We last summer I struggled to find out the flood map, even the satellite imagery for this domain, but I could not find it.
I see that. That's what it's gap.
That's what I was gonna say. That I mean, this is nice, very nice. But when you talk about accuracy and more, better than more other, I think it's nice if you compare that with some actual flood that happened with flood extent. That makes a little more sense.
And the main purpose of this study is not just for particularly setting up models for a particular flood event to say, so it was calibrated with an observed flood event. It was just, one thing is to see how much geophysical detail would affect the flood maps in different types of flood models like physical and semi-empirical, and comparing semi-empirical models together.
Yeah. All right.
Did you calculate that hand by yourself, or did you?
No, it is a multi-task effort. So I took the part of HEC-RAS 2D. Jing, who was the other member and was the student of Dr. Maidman. What's that?
Fernando or
He worked on the hand, and Dr. Tavakoli worked on the auto round.
If you use pre-calculated hand breathe, and you will make some errors, especially when you use after you repeat the bathymetry, so that will not account into the hand contours.
Yes. This is what I also talked with Jing about that how come that hand did not handle some high variation of special attributes, and for example, we find somewhere that if the elevation changes, you may find some lakes out of nowhere, and that's one of the discrepancies.
To go very good presentation. Lots of work.
Sure.
But one point maybe add maybe because think of the 2D is the HEC is a very complex model. You're adding when you implement that kind of model, you put lots of uncertainty into the model. Whereas the other is simple. So sometimes maybe that uncertainty.
I think the model like HEC-RAS must be applied in the lower, smaller domain than larger scale domain, because it's either labor intensive to be set up for a large scale domain, but in small scale domain.
High details.
Yes.
I'll join tomorrow.
Sure.
So when you are working at CONI, who's your advisor?
Balash Fekete. He was here last summer.
All right, see you. See you.
He developed the national water balance model plus that's the global model.
Yeah. I was there maybe 2014 or 15. I did the presentation.
In HIC, Hydroinformatic Conference.
Yeah.
Because I was a coordinator in that conference.
So
I met a lot of people.
What is the? Who is the head of the? There's a CONI. No one.
Reza Hamidari.
Yeah.
He's my advisor too.
Oh.
Yeah.
Yeah.
He's head of NOAA-CRAS.
NOAA-CRAS, yes. I was there and I did the presentation.
Yeah.
Yeah, I met a couple of people.
He came here maybe a month ago, 2 months ago.
To the UA?
To UA. I mean, it was the National Water Center. They gathered all the NOAA people, and maybe they need to propose their projects, future projects, and he said he's going to
I
come.
see. So you will be here, correct? You will be here, yeah. You will be definitely here.